So I'm Jianjun here, and it's a real pleasure anytime the graduate student attends. And Alexander is one of the very, very best students that I've ever had. And so I am really privileged to be here today to listen to his synopsis of his work. I've had some great students, not a lot, but one of them is one of my former students, Luke McGuire, who most of you know. And so I would put Alexander kind of similar in the same company as Luke. So that tells you something about anyone who's heard me talk about Luke and how impressed I am with his science should tell you something about how I feel about Alexander's science too. So Alexander got his BS here at the University of Arizona. He's done internships with USGS. So those are basically his main training along the way. Has been a combination of survey work in here at the U of A. And basically his work is really cutting edge in a couple of ways. One is that he does fantastic coding. He works with really large data sets, often global data sets. We'll see some examples of that. And he thinks very deeply about how to do things properly and efficiently, both in terms of accuracy and also in terms of being able to do high throughput computing of various kinds. In terms of looking at the entire parameter space of the model in order to find a global optimum solution, or being able to do all of the Earth at very high resolution to capture all the heterogeneity at various scales. So I think there's some really novel elements of this work that are going to be more important in the future as we look at the local effects of be able to forecast the local effects of climate and land use changes. So with that, pass it over to Alexander.
Okay, well, thanks everyone. Thank you for being here. It's a pleasure. It's an honor. It's been a long time coming, and I'm very glad to be here today to share my work with you, which I am very excited about. And I'm going to work through. And I like to have a timer. There's no timer up here, so if I'm getting close, someone just let me know. Thank you. Okay, so just a brief outline of where we're going with this presentation. We're going to start with some background information. There's people from diverse backgrounds watching this, and I want to make sure we all have at least a reasonable baseline to start from. And then we're going to move into my 3 chapters in my dissertation. The first one is a probabilistic debris flow hazard assessment methodology. The second is a novel method for overland flow routing over digital elevation models. And the final one is projected changes to suspended sediment yield in global rivers. So starting with the first background information. And one last outline here, just the sections I'm going to move through fairly quickly. So briefly with numerical methods, which is what I knew with John and Luke and a lot of people in this group, we use algorithms and computers to solve problems related to the earth sciences. Problems are often involving nonlinear quantity, which make them hard to predict without some sort of iterative algorithmic way to move forward. So one example that some of you may be familiar with is the heat equation presented here in the center, where our change in, say, heat with time is a function of the second derivative of that variable in space. And finally, we often use iterative methods in solving these. And there's a lot of different ways you can do iterative methods. One example that I've shown here is using what's called fixed point iteration, where our n plus first guess of this quantity x is some function of the nth version. So every time we get a new guess, we plug it back into the function, we get a new guess. Right? With the idea being, with a well-posed problem and appropriate numerical techniques, there is some fixed point in the space where once we arrive at that solution, applying the function to that value returns the same value. Another thing we're going to be using in all 3 chapters are grids. And grids are basically a way to discretize the Earth's surface into disjoint units. And then within each unit, either viewing these as cells or as nodes, we compute quantities for that node or cell. So here on the left is a pretty coarse resolution grid covering the state of Arizona. On the right, showing a zoomed in view of Tucson, and this finer grid, which is a 30 arc-second grid here, and shows how we break up Tucson and the mountains into these grid points. I'll return to these. Another thing that pops up in all of these is flow routing. So with that discretized view of the Earth, flow routing methods are simplified ways of modeling how different quantities such as water, sediment, pollutants, energy, how those move through the landscape, how they collect from the highest mountains, travel down through channels, and eventually end up in an ocean or a lake, delta, what have you. Yeah, so we generally start at the highest elevations and move things downward. On the right here is a figure from John's book showing two different flow routing algorithms. This one on the left, which is the top figure, shows the steepest descent, or also known as D8, I'll refer to it as D8 later, flow routing method, where we take everything from one node and we pass it to one node downstream, and that node downstream is the steepest descent. Whichever one has the steepest slope going down, that's where we send it. The second is called MFD, multiple flow directions, which is exactly like it sounds. We take everything in one node and then we distribute it amongst the downstream neighbors. And in rectangular grids, which is what we'll use here, that's 8 possible neighbors that we can send material to. In really steep places, MFD can also end up directing everything to a single node, but it gives you the flexibility of distributing it across the surface as well. And the generalized output we get from this, which we can use to compute other quantities we're interested in, is the contributing area, which essentially, if you stand at a point, say in a river, and look upstream, all of the area that drains down into you, that's contributing area. That is a length squared scale. One quantity we'll use later is the specific contributing area, and that is contributing area divided by the width of your flow. So it's like how much contributing area is passing through a zone per unit width. So combining those two that we just talked about, grids and routing, we have Tucson again, and this is elevation on the left, the DEM, and then a D8 routing from that. So you can see, you might recognize Santa Cruz there. This is the Rito River, the Sabino Canyon shows up faintly. And so this routed area, you can see in the colors a little bit, but it scales over multiple magnitudes, from the smallest drainages of a few square kilometers up to scale of the Amazon over 1 million and plus. One last flow routing method we'll talk about later. It's called the D-infinity flow routing method. This is a popular flow routing method because, as implied by the name, you can distribute flow downstream in any direction between angles of 0 and 360 degrees. And what that ends up doing is, through some equations we don't need to go into too much here, but it distributes it, say on this vector here, it'll distribute your flow between those two downstream zones. And so if you do this over a wide area, you can have flow distributing again, but also convergent in steep convergent areas. So this method was originally introduced over 25 years ago to counteract what was deemed as unrealistic dispersion of that MFD flow routing method. The authors argued that MFD spread things out too much unrealistically. So we'll come back. Okay, lastly, and this is an area that I've gotten into in the last year and a half, and I'm still learning a lot about, but it's pretty exciting, I think. And I know a lot of people here have used it in other realms, and I'd love to hear thoughts after or later if you have it. But using Bayesian calibration techniques, it provides a systematic way for us to incorporate uncertainty in our observation data, as well as uncertainty associated with the assumptions we use to create models, the uncertainty underlying the model structure itself. A lot of those uncertainties we don't really know ahead of time, right? Right, with data, when you're taking measurements, you generally have an idea like, say, taking a temperature, yeah, it's probably going to be this value plus or minus some percentage is the true value. Right? So we incorporate that into the calibration of model parameters. Up in the top right here, I've given a little sneak peek of future slide showing how we have these two on the left. These two figures are sum of residual sum of squares of two different calibrations, and we combine the information from these two to end up with a centralized distribution shown in this plot on the right, which we can then sample from randomly to represent uncertainty associated with what those parameters should actually be. We do this using Bayes' theorem. Here P is probability, and just briefly, this item on the left is the posterior distribution of some parameter theta, that is our model parameter, y1, y2, etc. are observed data. So this is saying, what is the actual probability of a given model parameter given what we see in the data? It's proportional to what this term here, the reverse of that, the probability of the data given what is the true parameter multiplied by this, which is a prior, which represents our prior understanding of what those parameters should be. And then what we'll end up doing with this term here, which we generally don't know, we can substitute something that's proportional to it, which is the likelihood function of, given what we observe in the data, how likely is it that any given parameter is the true value. So I'll present two different ways that we've done this. One using a traditional likelihood function with normally, a maximum likelihood estimator, assuming a normal distribution of the data errors. The other, we use an expert elicitation methodology to choose what those probabilities should be. Okay, we've made it through the background. So we're going into the first chapter, and this is a work that is under review with the Natural Hazards and Earth System Sciences Journal. Titled Probabilistic Assessment of Post-Fire Debris Flow Inundation in Response to Forecast Rainfall. I worked on this project with Luke here in the room, as well as Kwang Seung-Jun in the Department of Computer Science, Kitty Barnhart, the USGS, and Nina Oakley in California Geological Survey. So to motivate this a little bit, this image in the top center showing the 2017 Thomas Fire, which occurred outside Los Angeles between LA and Santa Barbara. Essentially, it burned over 1,000 square kilometers. Before the fire was fully contained, an early morning storm on January 9th, 2018 passed through the area, and that's what this figure on the right is showing, with the red values being intense rainfall. And if you can just see the red outline here is the Thomas Fire burn area, and this is from Nina Oakley's paper in 2018. What that intense storm did was drop a lot of rain very quickly on burned basins, which mobilized a lot of sediment boulders that traveled down the canyons of the mountains, exited the mountains, and entered the alluvial fan where people like to live. And this image is from that event. Those rocks and boulders weren't there before. That is a newly buried house from this event. So when we have wildfire and we have rainfall following wildfire, because of changes to the watershed hydrology that fire does, we get more runoff, we can have greater erosion, and these things can magnify each other and result in really destructive impacts. So this was a sad event. A lot of people died, were injured, homes were damaged. And the thing is that the agencies knew it was coming, they were prepared for it, but the magnitude of the response of the watersheds was unforeseen. And so this work is an effort to try to address that gap and help predict where and when these things might happen with a little bit more uncertainty in the future. So this is a figure that many of you may have seen before. We use it a lot in this group. With debris flows, when we're thinking about after wildfire, where they might happen, there's essentially three, we can subdivide into three sections. First, how likely is a debris flow to happen? This is a model output of an existing model that the USGS uses, with the red colors here indicating high predictive likelihood that a debris flow is going to happen in these watersheds. So these gray lines in here show individual watersheds, that the contributing area that drains to a point down here. Flow in all of these figures is from the top to the bottom. Here's the ocean down here. And this whole area in here is developed with homes, businesses, etc. Second part of the how we need to think about this is how big those debris flows are likely to be. And there's another established model USGS uses for doing that. So what we're interested in is once we have those, how big, how likely, we're interested in modeling how far are they going to run out. These polygons here show the observed deposits of debris flows after the event, where geologists went out and mapped where these things went. And that is data that we're going to use in this study. So our objectives: combine existing models of postfire debris flow likelihood, volume, and runout with a forecast of rainfall to generate spatially distributed inundation predictions. And in particular, predictions that incorporate uncertainties. We apply this modeling framework at the Montecito site where that deadly destructive storm happened. And we use an ensemble of atmospheric models from Oakley et al. 2023 that were designed to simulate a 24-hour lead time forecast that the National Weather Service might generate in advance of a storm. So we did this all after the event, but that atmospheric model ensemble was set up as though it was before the event. And finally, we quantify the relative importance of key input parameters to each of these models via sensitivity analysis. So the debris flow runout portion of this that we use is Alex Sporer's work, ProDF, which is the progressive debris flow. I don't remember the rest of it, but runout model. Yeah, essentially. So what this does is it iteratively builds the debris flow surface through time using a series of equations, which I put up here, and I won't go through them in too much depth. Come tomorrow if you'd like to know more about that, I would say, for Alex's talk. So first, they are solving conservation of mass. They use these empirical equations from Rickenman, 1999, to get at what is the predicted debris flow peak flow depth, which is updated iteratively in small increments. So every time the debris flow depth is guessed at, we add just a fraction of that to the surface. Finally, we only route things downstream if the basal shear stress of the flow, which is computed as a product of flow density, gravity, depth, and the slope, exceeds some critical yield stress. So every simulation of ProDF requires specification of 3 input parameters, as we're doing here. 2 of these, the chi and tau, relate to flow mobility, essentially how deep is the flow going to get and how much is it going to spread out laterally. And the last one is the debris flow volume, how much stuff is moving into the watershed. And this figure is from Alex's paper showing in cross section what this iterative building technique looks like. So the existing models of debris flow likelihood and volume that we use are the Staley et al. M1 and the Gardner et al. EAV models, respectively. These models are functions of topographic metrics like steepness. They're a function of soil burn severity. They're a function of how erosive the soil is in the watershed upstream. And lastly, they're a function of the peak 15-minute rainfall intensity, which is essentially how much rainfall falls in 15 minutes. So in this modeling exercise, we computed the likelihood and volume with the upstream properties fixed, and we varied the I-15 rainfall rate using the forecast values. This image on the right just shows the range of support once we have a prediction, which a prediction of volume given in I-15, which are these black dots. We assume a log uniform range of support around those, which is large, but is consistent with the model and the data that it was fit to. There's still quite a bit of uncertainty when it comes to predicting debris flow. So when we simulate, we don't just use the predicted volume value, we sample from that whole range of support. We take a value randomly and simulate. So about the atmospheric models briefly, here's just a slice of a time slice image from 4 different members of that 100-member ensemble showing rainfall rates. This red box shows where our study area is. So these models are pretty high resolution in space and time. They output precipitation in 5-minute increments, which for our study, we then averaged over a 15-minute window to find the peak 15-minute rainfall rates. And this figure in the bottom right shows the full distribution over all of the watersheds that we studied. The I-15s extracted from the atmospheric models. These dashed lines are the observed peak rainfall rates from that storm, which gives you an idea of how extreme that storm was, and we'll come back to it. So now we're at the Bayesian calibration portion of this. So just moving through this step by step. We start with a uniform distribution over the 3 input model parameters, which we keep for volume, we don't change that. But for chi and tau, so essentially we're saying we have no information. Every possible value of these 2 parameters is equally likely. We then update the posterior by calibrating ProDF to 4 out of the 5 watersheds. And we reserve the 5th watershed, which is shown on the right here, for validation. So in doing this, we use the similarity index as our objective metric, which varies from -1, which is a complete misfit, to 1, which is a perfect fit between model and observations. So this plot in the bottom left here is showing the 1. So we're showing the flow resistance coefficient chi on the x-axis and yield strength on the y-axis, and each of these pixels is colored by how ProDF performs at this event using that particular chi-tau pair. So we get what's called a response surface here. Yellow values indicate better model performance, blue indicates worse model performance. So this is not what's traditionally used in a maximum likelihood estimator objective, is the sum of squared residuals. This metric is different in that it is on a bounded range. It goes from -1 to 1. So the way that we got from this to a probability in the posterior is we extracted individual ProDF simulations and their mapped outputs, so something like this for each of these runs, and then gave a full panel showing a whole bunch of these to experts, all of our co-authors and a few other people in the field. And everyone individually decided where we thought the model performed half as well as the best model in the entire range of values. And remarkably, we all agreed. I haven't showed it here, but we all picked the same level, the same contour level in this. So we have some high confidence in at least our expert opinion of what model performing half as well is doing. And finding that one value, in addition to having this response surface, allows us to specify the full posterior distribution. And in the bottom right, this figure is showing samples generated with Markov chain Monte Carlo, and our expert elicitation of where that probability lies. So this thing on the right, these are values which we will sample from for every simulation. And by doing that, we will recreate this distribution in the output in terms of which parameters we use. So the forecast simulations we ran 50 simulations for every ensemble member. And every one of those simulations produces a binary inundation map, which was shown on the last slide. And then when we average all of those together, we end up with a map of values between 0 and 1. Right? So a binary inundation map is essentially 0 everywhere where there's no inundation, and 1s everywhere where we predict there will be inundation. summing those all up and dividing by the total number of them gives you a value between 0 and 1, which we interpret as a model prediction of probability of inundation. For comparison, we also ran 2 simulations with static volumes, which are termed scenario A and scenario B, one using the actual observed event volume, which is what was measured in the field by geologists, and the other is a volume computed using the Gardner et al. Equation with the observed values of the I-15 precipitation. Okay, so these are some of our primary results. This map on the left shows the probability of inundation with blue colors indicating low probability and yellow 50-50, and then red being 100% confidence of the models that that area will be inundated by a debris flow in response to a storm. The black dashed lines on this show the outline of the observed inundations. So in general, we see that the model predictions at the 40% maybe and higher level do capture most of the observed inundations. But if we look at the images on the right, see that there's only very few places where the model is confident that the debris flow is going to happen. Even at this top one is everything greater than 84% likelihood. This middle plot is everything greater than 50% likelihood. And even that is clearly underestimating the observed inundation. We have to get down to about a level of 16% likelihood to match what was observed to happen. Another way of looking at that briefly are these plots down here. This is called a calibration curve. If the model was operating perfectly, these points would lie directly along the one line. Because they're above this line, it's an indication that the model is under predicting inundation. And this plot here is a histogram of the forecast probabilities. Ideally, a perfect model would have all zeros and all ones. It's either 100% confident nothing's going to happen or 100% confident it is going to happen. So generally, in these sorts of plots, you want to see a U shape. Clearly, we don't see that here. So we have to wonder why is that. If we look at those 2 scenarios of static volumes, on the top here is the observed volume, on the bottom is the volume predicted with I-15. You can see we have much larger inundation probabilities across the simulation domain, especially within areas that were observed to be inundated. See from the calibration line that the model is doing a reasonably good job of matching forecast probabilities with observed probabilities. And we're starting to see that U shape that I was talking about. We're getting more confidence that something is going to happen or nothing is going to happen. So our interpretation of this is that it's due to the extreme nature of rainfall in that event. It's this, again, this distribution is showing what the atmospheric models were predicting. They are undershooting it. The observed values are in the far upper tail of distribution. And we think that showing these scenarios confirms that. If we use the observed I-15, which is in the bottom here, the Gardner et al. Equation with the observed I-15 over predicts what the observed volume was. And we can see that in the model response here. We get this line dropping below the 1-to-1 line, which means the model is over predicting inundation. Okay, lastly on this chapter is a sensitivity analysis of each of the model parameters. Here's the flow resistance, the yield strength, and volume. What these plots are showing is how sensitive inundation in a given location is to each of the model parameters. So low values mean that inundation at that location is just not sensitive at all to that parameter. Dark colors means that it's very sensitive to that parameter. And in the bottom right, we're showing the maximum sensitivity index of each parameter in every pixel across the domain. So we can see some clear trends. First, the volume in the bottom left here has clearly the strongest control over most of the domain. But in certain locations, depending on where you are in the landscape, the 2 flow mobility parameters can also be important. And we find that overall, all 3 parameters are significantly important, but the volume dominates. So, in conclusion, we introduced a methodology connecting existing models of postfire debris flow, likelihood, volume, and run out with an ensemble of atmospheric models to produce probabilistic forecasts of debris flow inundation. We found that all three ProDF input parameters were significantly important, but that each may be the most important locally. And overall, we found that the input debris flow volume exerted the strongest control on inundation outcomes. So a conclusion from this is if we want to reduce uncertainty in where these things are going to go, we have to reduce uncertainty in the debris flow volume, more so than the others. That's major conclusion. Okay. We're going to move into the overland flow routing. So this chapter is it's entitled An Evaluation of Flow Routing Algorithms for Calculating Contributing Area on Regular Grids. This is work that I worked on with John, as well as Satya Chatat and Sridham Ananthanarayan at the BHP Technical Center about Excellence and Legacy Assets. And this is a manuscript we are very, very close to submitting to Earth Surface Dynamics. So just some motivation for this project. I was motivated on two fronts. First, for a long time, we've been wanting to better simulate overland flow and landscape evolution models. Landscape evolution models work over timescales of thousands to millions of years, and running highly sophisticated water solvers like even the shallow water equation solvers on these topographies is just too inefficient to be realistically useful. Secondly, on this site, this hill slope here, which is it's a steeply sloping hill slope with from the top of the screen to the bottom. In attempting to calculate specific discharge across the slope, we're finding that depending on how the hill slope was oriented in the model, so here it's perfectly horizontal, and here it's just been rotated 30 degrees, the output of the specific contributing area of D infinity produced drastically different results. This is a specific contributing area where when it's oriented along the cardinal direction where the flow lines are coming straight down the slope, we get much larger values than if it's rotated. Comparing this with the MFD flow routing algorithm, which doesn't seem to have the same grid orientation effect. That's what led us down this road. So a brief comparison of these, the D infinity and the MFD flow routing method on a few analytic test cases. This first one is a plane that's it's a sloping plane oriented, so flow is moving in this direction. This surface is a cone where we have the highest elevation in the middle and it's a planar surface going out. And the opposite of that in the bottom, where it's a cone, but it's an inverted cone like an ice cream cone. The flow is moving towards the middle. These are showing the D infinity results. First for contributing area in this specific contributing area in this column, and then error between that and the analytic results in this column. And that bias along the ordinates and the diagonals is clearly evident. It shows up in the error of these as well. And then just completeness, comparing that with MFD, we do see some error, but it's not oriented along these directions in the same way. And these plots are just demonstrating that where D infinity differs from the analytic by more than MFD, and in this bottom one is absolute error, showing that D infinity error increases. This is a log scale, it's an order of magnitude higher in some cases. Okay, so this is something John and I have worked on for a long time, and it's gone through many different versions, but we've settled on this version that we think works pretty well. So what I'm going to walk through in these next slides are the basic algorithmic steps, where we're going to route flow using the water surface slope instead of the bed slope. And we're going to use a modified version of the MFD algorithm to do that, where we iteratively update the surface. In many ways, it's similar to the ProDF algorithm in that we're incrementally and iteratively updating the flow surface. But in this case, water instead of debris flows. So to get us kind of on the same page, here's a simple diagram showing a bed surface with an elevation Z, and then water on top of that at depth H, flowing in down to the right, water flows down slope. And then when you see this symbol, this is nabla z plus h, it's the slope of this water surface, the sum of these two things. How is that surface slope? We solve the steady state conservation of mass, with Q being unit discharge and R being a runoff intensity. So think of that as rainfall falling on the ground and running off. We use Manning's equation in for the unit discharge, and what we'll end up doing is solving this for the flow depth H, and rearranging these terms. N is Manning's coefficient. I think I covered everything. Okay. Couple equations here. This top one is how MFD weights are predicted. Here, S is the topographic bed slope. So essentially, when you're at a node and deciding how to partition flow amongst your downstream neighbors, MFD says you do it by taking the bed slope raised to a power key and then dividing it by the sum of those. Right? So these values are going to be, if a node is upstream, where we're not going to send anything there, that's going to be 0. So any downstream neighbor we use in this equation. So these fractions will sum to 1, and it gives us a way to partition discharge downstream. We modify this instead to use the flow depth H here and the water surface slope instead of the bed slope here. And we raise them to these powers corresponding to powers from Manning's equation. Now, it's not something we've looked at, but theoretically, you could use alternative values for these powers, such as from the Shazy equation or others. There's literature suggesting they can vary over a range between 1 and 2 or 0 and 1 for both of these, but we've only considered these, and it seems to work fairly well. We raise everything to the 2p so that we recover this relationship that Freeman found works best for distributing flow amongst the landscape. So in the end, we'll have water surface slope raised to the p power. Now, this is slightly simplified. We've actually implemented it so that the Manning's equation n can vary across the topography, in which case it would just be divided by the local n in IPGs. So some pseudocode for how this works. We do the following in every grid pixel across our grids. We guess an initial water surface by routing using MFD and Manning's equation using the bed slope topography, which is now Z. And then we have two different loops here. This outer loop determines how many times we're going to completely reconstruct a water surface. And the inner loop determines how many small increments we're going to use in each of those constructions. Right? So first we calculate our specific discharge in each pixel before routing, just as the sum of our rainfall turned into a volume plus our lateral inflow, and there should be a delta X here that we're using a volumetric discharge for this portion, but in any case, we then calculate the current estimate of the water surface slope, and then we start at the highest pixel, work our way downstream, and we partition discharge using those equations I showed on the previous slide amongst the neighbors, so that we're distributing discharge everywhere. And then at the very end, we come back and we compute the flow depth using Manning's equation with the current guess of the water surface slope and this new discharge we just computed. And we add just one fraction, 1/NA fraction of that guess of H to the current water surface estimate. So some results, and then I have a graphic way of showing how this thing actually works. But first, an assessment of this new IDS flow routing methodology. So first on the left, we have that hill slope here. On the top is showing results from Flow2D, which is a proprietary software that solves the shallow water equations, is commonly used in applications, and we treat it as the state of the art here. On the bottom is the results of an IDS algorithm with the same runoff intensity forcing, and visually you can see the results are similar in terms of just a contributing area. If we compare our specific contributing area for flow 2D as well as IDS, as well as the other D infinity and MFD routing methods. D infinity we show as this large difference here. MFD is staying pretty close to it. Flow 2D, the state of the art, is this solid line here. And then the IDS algorithm is this dashed line right next to it with the same runoff intensity forcing. We also compare it to an analytic solution of the shallow water equations on this imaginary slope, which is flow from the top to the bottom. We have a restriction in the channel width, and as you can see in the bottom, the topography of this bed is not constant, it changes with time. And again, the dash, so that here the dash line is the analytic solution, and IDS closely approximates it. Yeah. Okay, so to give you an example of what this algorithm is doing, we're using a real world topography here. This is Lucky Hills watershed area, the Walnut Gulch experimental watershed. It's near Tombstone, Arizona. So what we have in this this area, we have a local high area, we have a few convergent channels, one large channel, and then we have some rilling going on up into these highlands. Now the colors indicate there's a lot of elevation change here, but if you look right here on the right, it's really 20 meters difference from the bottom to the top, so it's not as extreme as it seems. On the bottom here are maps of flow depth, and in particular the logarithm of flow depth, so that we can see how flow depth changes as we get into these smaller drainages higher up on the mountains. In these figures, it's slightly rotated. The high area is here, and this is that primary drainage. The image on the left is showing our initial guess, which was just using MFD and Manny's equation. You can see, especially down here, we have flow localization in this primary channel. And then on the right is our final depth output, where the water surface has smoothed out essentially and filled in the channel to either side. So this is a quick animation of how this works. I'll let it play a couple times, moving from the first iterate all the way to the end. You can see we slowly essentially diffuse out that high depth area across the whole area. So real quick, in this example, you may have noticed we used a 500 millimeter per hour forcing, which is constant, which is not realistic. That would be an incredible rain event, especially if it lasted for anything more than a couple minutes. But I used it here just to demonstrate how when we get into this low sloping area down here, the water surface slope is really flattening out. It takes longer for the algorithm to converge in those areas, which is to be expected. I'm not going into, but Manny's equation and equations like it are known to be degenerate, it's called. As you get close to either no flow depth or a flat water surface, the equations just start to blow. So it's able to handle them, it just takes more iterations. And lastly, briefly, as I mentioned just a second ago, this equation, we can have different powers to it. So with this particular equation, we're linear in both the depth and the water surface slope. This is known as the Boost-Netzke equation, which I'm realizing I didn't write on there, but it's all the same anyways. This is applicable under very specific assumptions about the groundwater table surface slope and the conditions in which aquifer exists. So this is just to show how we can match the analytical solution by solving for this set of equations instead of our Manning's equation, and a prediction of not only depth to the water table here, but also how we can use that in the product of depth and the water table slope, which is proportional to flow rate. Yeah, it's proportional to the flow rate of the problem. Okay. So in summary, we reevaluated the performance of the D infinity and MFD flow routing algorithms and demonstrated a bias of the D infinity along cardinal and ordinate directions. We introduced this novel iterative flow routing algorithm, IDS, that solves the continuity equations for flow depth and water surface slope. And we showed that it can closely approximate an analytical solution, and it does well in approximating solutions provided by a state-of-the-art shallow water equation. solver. And I just realized I didn't talk about this, but we also did a scaling study where we increased the total number of nodes in the grid and looked at how long it takes for the model to compute as you increase the number of nodes being used. The underlying algorithms that we use in the code have theoretically optimal scaling rates of n log n, where n is the total number of nodes. And that chart that I guess I can just show real quick here. This chart shows that we match that theoretical scaling most, which is good. That means it's coded as it should. Okay. So that is the end of that chapter. Moving into the final one. How am I doing that?
Yeah, about 11, sorry, about 11:50.
That's where we are right now. Oh, okay. We're gonna fight it this week.
We started about 5 minutes late, yeah, but you don't wanna.
I'll pick it up. Keep going. Okay. So this last chapter, this is a problem I've been working on for most of my time here, and it's very, very satisfying to be here presenting this all with you now. So this is titled Climate-Driven Changes to Background Suspended Sediment Yields in Global Rivers by the End of the Century. And in particular, we're going to look at the role of sediment detachment. I pulled these two images off the web just to give you an idea of the diversity of rivers across the globe. There's of course much more diversity than this, but on the left, we have Elwha River in Washington that drains the Cascades. As you can see a lot of cobbles in here, boulders, and judging by the rapids, you might think, well, this is probably a steeply sloping river. On the right, we have the Jianjun River in Western China, which is a heavily silt-dominated river. You can see that in the color of this river. And so in this, well, we're on time. I'll just move forward. I'll talk about it. Okay. So we're interested just to define a few things. First, if you see Q sub S, that's the total suspended load. So that's how much mass the river moves in a given year. S sub Y is the suspended sediment yield, which is the total load divided by the upstream area, which gives you an idea of in the average upstream area, how much sediment is coming out of this watershed. And finally, this I'm just going to refer to it as P, but with the subscript of 0.065 millimeters here, that's the fine fraction of the flux. That's the portion of the total, the suspended load that has a grain size of 62.5 microns or smaller. So this is how much of a given river's load is silt or finer versus how much is sand or coarser. So briefly, there's been a lot of work on suspended sediment yields because they vary over so many orders of magnitude across the globe. People have found that they're mostly controlled by each of these things. So we think that, well, each of these things are important and it depends on where you are. Lastly, humans have had a huge impact on suspended sediment yield across the globe. Here, because we're interested in background rates, we've done our best to control for this. Realistically, there are going to be human impacts in these data sets, but we're trying to get around that. I'll talk about a bit about how we've done that. So we use the suspended sediment flux model of Pelletier 2012, which explicitly differentiates between sediment detachment on hill slopes and transport through the channel network. In this way, we're able to connect sediment sources, which tend to be mountains and steeply sloping areas, with rivers and their mouths, which tend to be especially large rivers, tend to be much lower slope areas. So our research objective is to use forcing from global climate models or Earth system models to predict how suspended sediment yield might change in the future under different changes in climate in terms of temperature and precipitation, as well as vegetation cover in the different forcing pathways. So I've used three what are called shared socioeconomic pathways here. These are standardized ways for us to talk about different possible futures. SSP1 is a sustainable development future where emissions are drastically cut. SSP3 is a regional rivalry model where development happens and it's not the highest emission scenario, but there's still high emissions around. And then SSP 5 is the very high emission scenario where it's just business as usual for the next century. And then we use this assortment of models because the high resolution data that we're going to use in this high resolution global model is what's available for those models. Okay, briefly, this model shows how rainfall on a bare surface can lead to soil detachment, and once it's detached, if there's flowing water, it can get carried downstream. In steep areas, this can also happen through landsliding, etc. But in our model, which is about a kilometer scale resolution or finer throughout the globe, we calculate detachment according to this function here. C1 is a model parameter. F sub d is the fraction of soil in a given pixel, which is a grain size d. So we're going to transport, we're going to detach and transport sediment based on its grain size. Rho sub b is the bulk soil density. S is the topographic slope raised to a power. This is because we tend to see a nonlinear increase in detachment as slope is increased. And then we sum over the product of rainfall and the exponential of e to the minus LAI, which is the area index. Without going too much into it, detachment has been known to follow these two relations. We use the product to account for seasonal covariance between these two, right? Because when it's rainier, you tend to get more vegetation, which protects the land surface. So those two, the covariance between those two are important. And we use temperature in this to essentially say if a given month the temperature is less than 0, then everything falls as snow, and we don't have detachment in that month. So it's pretty simple representation, but we're using the mean monthly values here. Briefly, just to show some grain size differences from, give you an idea, from my own backyard, this is a lot of silt and clay. You might be able to see a few sand or maybe tiny gravel pieces in there. And then our dog Mika loves to roll in the dirt and gets covered in the fine fraction. So, okay, okay, so the browse for the transport portion of this model, we use a modified Rouse number. Essentially, the Rouse number is a ratio of for a given sediment grain of diameter d, the settling velocity, how quickly that grain is going to settle out of column, to what's the product of the von Karman constant with shear velocity, which is proportional to the vertical velocities that you'll experience due to turbulent fluctuations in the flow. And we use a modified Rouse number here where we just account for slope in the denominator. Normally there would be a flow depth here as well, but we do this on the justification that slopes vary over a large range of magnitudes, while flow depths at high flow conditions vary over only about 1, maybe 2 orders of magnitude. So we incorporate that discharge hydrology into the C2 parameter in this sense. And finally, if this number calculated as the settling velocity of given grain size over the slope times the C2 parameter is less than 1.2, then we say it is transported downstream. Otherwise, it does not. Briefly, we use 4 observation data sets, 2 of them global. In each case, we reserve 1 data set for calibration and the second data set for validation. For the global scale, we have the suspended sediment yield as our objective metric. And in the second set of data sets, we use the fine fraction of the flux as our target metric. In both cases, the calibration data set is an independent data set that has been selected. These sites have been selected and corrected for human impact. So we're hopefully getting mostly natural impacts in these measurements. The validation data sets, on the other hand, have no control for human impacts. So we expect those to show up in the form of additional scatter in our plots. Here's just a visualization of some of the input rasters that we use. This is not all of them by any means, but we have our digital elevation model here, topography, slope, percent of soil around the globe that is silt. We have equivalent data sets for clay, sand, and gravel. Then monthly precipitation, vegetative cover in the form of leaf area index, and mean temperature. So for the future, these are examples from GFDL SSP 5.85 scenario showing expected change is a ratio of leaf area index, precipitation with red colors here being decreases and blue colors being increases in monthly precipitation and changes in temperature. So we're going to use these to drive the suspended sediment flux model and compare it with what we do in the historical case to see how things are expected to change. Since we're low on time, I'll just say we do Bayesian calibration of model parameters here. We incorporate both of those calibration data sets. One of them for using just the US data as a prior and then combine them into the full posterior in this step. We use the log likelihood function of maximum likelihood estimator. And following the recommendation of Aaron et al. 2019, we set sigma just as a constant range. So the range of data divided by 4, which without getting into it comes from an assumption of normally distributed errors in the data, which results in sigma values of 25% for the fraction of fine flux data. And for the global rivers, we work in log space and it works to about an order of magnitude of 17. The calibration, there's a lot of information here, but essentially I will just say that in terms of all 4 data sets, we find significant correlation between model predictions and observations. The range of scatter here is not surprising, given simplifications in our model and as well as the range of suspended sediment yields observed across the globe. And even with the data that is known to have human impacts in it, we still perform okay. And this is that same plot from before of our Bayesian calibration. So I think I'm about out of time, so I'll fly through these results, but just showing you some global projected changes we have here. This is the median change in suspended sediment yield at river stations in all of the global river data sets. See that in SSP1, there's limited change relative to the 2 other scenarios, which you might expect given these are greater changes in climate conditions, and that SSP3 and SSP5 have some similarities between them, which I'll move into a little bit. So what we can also do is look at individual rivers and take, in this case, these are sorted by taking the average change across all scenarios and then plotting. The color here indicates how much change is predicted for that particular river. Red being increases, blue being decreases. So these are the 10 greatest increases and the 10 greatest decreases that we see across the globe. I'm going to look at some of these in more detail, particularly the Hudson River here. So we can also look at the full distribution of across all of the historical simulations and all of the future simulations, look at the distribution of what is the predicted suspended sediment yield in the future. And what this is showing are rivers where both of those distributions are disjoint at the 95% level. So these rivers have 95% interval for historical conditions here, and then the future conditions here. They don't overlap at all. Showing mostly these are projected increases where we have this significant change, with the exception of Southern Europe, which consistently shows decreases. By latitude, we can look at how these things are projected to change. Leaf area index is showing the greatest variation, especially equatorially, whereas precipitation changes in suspended sediment yield driven by precipitation are relatively modest, and temperature plays the largest role at high latitudes, as you can see. And yeah, so in this bottom right is the combined effect. You can see across the globe, it really depends on where you are, of what change you're going to experience. Now this has a lot of data on it. On the right are projected changes in leaf area index for these 2 scenarios. And I just wanted to highlight, which was surprising to me, that in all cases, one of the change in suspended sediment yield or the total load the change in the SSP3 scenario exceeds the others. Right, coming into this, I expected SSP5 to have the greatest changes because those are the greatest changes in climate. This is still something I like to look into more. I think it's because of increased global greening in these Earth system models, where just caused by CO2 fertilization. So I want to show a couple regional changes for specific scenarios, just to give you an idea of what these models look like. But this is a disclaimer, not saying that this is what's going to happen, or it's even the most likely scenario. So yeah, don't forget, right? Okay, so we're looking in the Northeast United States here, broken out by forcing variable, leaf area index, precipitation, temperature, and overall change. And if you remember from just a couple slides ago, this was an area of significant projected changes. Essentially, what we find is that changes in leaf area index and temperature drive the largest changes, but even precipitation is driving an increase in suspended sediment yield in these rivers. This bottom is showing the distribution of predictions. In black is historical, and then the colored lines are different models for each of the scenarios. And you can see how there is model consensus in these that we're moving into higher suspended sediment yield in these cases. In contrast, this is in northern Russia, draining into the Northern Ocean up here. And on the bottom plot here, we're showing the Ob River, which is located over here. In contrast, this is an area where temperatures are expected to increase quite a bit and increase suspended sediment yields. But Earth system models are showing a general greening of the area. Which ends up resulting in a mixture of changes. Right? So it's really a matter of where you are. Is your vegetation increasing or decreasing? It can either amplify or modulate the response. Okay, reach conclusions. So we calibrated this global suspended sediment flux model, multiple data sets. We used Earth system model simulation outputs to drive projections and for future changes, sediment fluxes in these rivers. We found that leaf area index and temperature drive the largest changes, with precipitation driving lower, but still significant changes. Interestingly, we found that SSP3-7.0 drove the largest projected changes, perhaps due to CO2 fertilization effects at larger gradient forcing. And I think in future work, I'd like to incorporate additional Earth system model results into this to gain some confidence, perhaps in where leaf area index is going to go. And I'd like to reevaluate our choice of sigma in this case, which I didn't really get into, but I think there's reasons to believe it's too small. And lastly, to look further at that SSP3. So with that, I just want to say thank you to everybody who's here, to my committee, sticking with me for all this time. My loving partner, Courtney, my parents who are here, John and Laurie, Grandma, if you're watching, hi. Rich, Leon, and Janice at USGS, with whom I had a wonderful internship. All my Frisbee friends who kept me fit, healthy, and sane this time, and all my fellow graduate students. Thanks so much for this.
So I understand that a few people may need to leave, given the hour, but I want to just open us up to questions for Alexander in the next few minutes, 5 to 10 minutes. And then the committee's going to stay and do a little bit more grilling as needed. So any questions for Alexander?
How do you think that like the US Geology Society can further your work, or is there an area that you can give them that you can determine needs to be looked at before another catastrophe happens?
Well, I'd say my first chapter is an area of ongoing research, very active area of research that USGS is really interested in. Surveys of the scientific community have shown people think something like this that shows spatial changes or spatial predictions and inundation that incorporate uncertainty, especially in forecast rainfall, is important. So I'd say that they're already doing the work. And from conversations with people, I think work like this, whether it's done by me or someone else, is going to continue.
Got one. Thanks for all the great work on uncertainty quantification. That's really important stuff. I had one about the forecast. You were talking about the differences between different climate, trajectories and those differences there. And you have some, I think, median forecasts for what the transport would be. But I wonder if you've had any investigation into how much uncertainty there is in those like overall distributions, not just the median, but
Yeah,
according to different climate scenarios. Have you had a chance to look at that?
a little bit, yeah. I think I should can in more depth. One thing I have looked at is global coefficient variation across models, which is a basic indicator of that. And it seems that the largest uncertainties with this model under these climate forcings is in equatorial regions, especially Amazon, Central Africa, where changes in vegetation especially they seem to go in both directions, depending on which model you choose. There's also some areas at high latitudes around Greenland that are showing some bit of uncertainty. But it's something that I would like to look at.
Sure.
If you have any ideas, yeah.
Well, as we have follow-ups of the spatial description there is really helpful. What about across those three different climate scenarios? Do you see any like additional uncertainty, say, with, or I don't know if you've had a chance to look?
Yeah. The higher radiant forcing did show greater uncertainty.
Yeah, I have a very nice talk and the idea model, you have with them. That's very impressive. The curious about its efficiency compared to the Shaolin model. And but the result is so close to that. Curious about the efficiency could be very good.
Yeah.
And the second question is where can we use that app? Like what kind of flow and what type of topography, and is that available for, let's see, the Colorado River? And how about the very big floods, like the neck flood, that?
Yeah, so let me start with that one. So Manning's equation is, derived with the assumption that the water surface slope is pretty close to the best. So that's where it's going to perform less. As you get further and further from that assumption, I know that work has shown that it can still work pretty well, but I don't have an actual assessment of that. So I think it works best. So in terms of performance, it definitely works best in steep sloping areas. And then just as in terms of converging to a solution as you get to lower slope areas or areas with a large backwater length, for instance, that it takes more iterations to converge, which means more computational time. In terms of efficiency, it definitely takes longer than MFD or D infinity, but it takes less time than shallow water equation solves. It's not really something I talked about, but I'm kind of obsessed with making things efficient. Computation, John mentioned it earlier, to a fault, I think. So I think the code we've written is pretty efficient in terms of how efficient we can make it. So yeah. It's also a question of how accurate you want your result to be. With more iterations, we get to greater accuracy.
You mentioned landscape evolution models. Do you see it being feasible for landscape evolution models right now, or do you feel like it would need to become even like a lot faster?
So I think it could, yeah. So the results that I showed there, which was a total of 40, maybe 100, I don't remember exactly, did a few different ones, but that took on my laptop 2 seconds to do on a 200 by 200 grid, which isn't huge. It's not small. So in terms of efficiency, yes. The one thing that we haven't implemented yet that we would like to work on is a width parameterization. Right now, it uses the full pixel width as the weighted channel width. So in landscape evolution models, once you get to those larger scales where width becomes a subgrid parameterization, we have to incorporate that in some way.
Good questions, thank you. Anything else? Okay, and thank you guys for coming, and thank you for the spread, the food looked wonderful, so. On your way out, please help yourselves, the committee to stay behind, and we'll talk to Alexander a little bit more. Thank you all for coming, I appreciate it.
Yeah. Brian?